robots in structural steel. Hello and welcome to today's Steelo podcast, where I'll be talking about our journey with introducing robots into structural steel, which is exactly what we do. So, robots have been used for decades in manufacturing, and robots are wonderful. They have the precision of 0.1 millimeter. They can do the same task perfectly. They have like almost 100% repeatability, something that a human just can't do no matter how hard you tried. So the question is, well, why haven't they been adopted in structural steel? And by the way, they haven't. It's one of the industries that is really lagging behind when it comes to technology. So with robots, again, they are great when it comes to repetitive tasks. Now, the majority of applications where robots have been successfully adopted is to do with high volumes. So, for example, obviously the automotive industry. You design a car and then you make 10,000 of them, so you only have to program the robot once, and then the robot just repeats that same task over and over again. So I'll go through almost like a list of reasons why it is very difficult to introduce robots into structural steel, and where are we with this and what my thoughts are on this topic. So one of the reasons is that structural steel is almost like bespoke manufacturing. Even if you have the same exactly the same type of beam fabricated, let's say it's a column for a warehouse, you'll probably end up with 10, maybe 20 of the same columns. So it's still very low volume for what is needed in order to program it once and have it going for thousands of the same tasks. But predominantly every beam is different, so you'd have to write a program for every single beam. Now, this is a futile exercise because you would have to pay a robot engineer to write a program. Obviously, there's some automation available, but still you need someone behind the desk writing that program, then uploading it onto the robot system, and then having someone on the shop floor operating the robot. Probably it would be the same guy from the office, and you probably still need a welder. So suddenly you need two people plus a robot. So instead of just paying a welder, you now have to pay the welder, you have to pay the robot engineer, and also the depreciation costs of the robot. So you, instead of saving costs, you're actually tripling up. So it really doesn't make sense. And that is down to the low volume of the same beam. Now, it's quite funny because you might be like doing 1 million tons a year as a company turning over, but still when you focus on a single beam, it's a one-off. The other reason, and I think this is the most important one, is that steel beams are very imperfect. So unlike machined items, which are machined down to, let's say, 0.01 millimeter, steel beams are all over the place, and you'd really be surprised as to how different each section is from itself. So let's have a beam, one of the sort of most common ones, 203 UC46, which basically means that it's 203 millimeters deep, 203 millimeters wide, and the shape is like an H section. So the possible deviations are, first of all, the depth can be different. So instead of 203 millimeters, it could be 205 millimeters, and that's still within accepted limits. Next, the flanges, instead of being parallel to each other, so the sides of the H, they might be skew, so inwards or outwards, depending how you look at it. And if it's only, I don't know, a degree or two, that means that the ends are out by 1 millimeter or 2, and that doubles up because quite often they are both sort of squeezed into one on one side, which pushes the other side out, and then that could easily go into 2, 3, 4 millimeters of intolerance, which obviously means that a robot will then struggle. Next, what could happen is those flanges, instead of being one on top of each other, they could be moved. So one is moved to one side and the other one is moved to the other side, which again could be still within acceptable British standards when it comes to structural tolerances, but for a robot that is unacceptable. Next could be the fact that the web is skew, so it's not exactly at a right angle compared to the flanges. It's actually at a slight angle, or the web is at the right angle, but it's moved altogether by a few millimeters. Now, robots, as I mentioned, are great for repetitive tasks, and robots, unfortunately, one could say they're quite dumb, because they only work based on what's been fed as a software, as a program. So it knows it needs to do this sort of path or follow a path, but it won't have a clue that there's a steel beam in the way. So this is the difference between robots and humans. Robots are very good when it comes to precision and repetitiveness. Humans, they're not so good in precision and repetitiveness, but they are very easy to adopt. So a human welder will never weld into a steel beam. They just know they need to go around it. So it's kind of obvious for a human, but for a robot doesn't have a clue. It just follows the predefined path. So because of it, you then have to be very, very, very creative. How do you get away with it? So what you could end up with is a situation where the robot follows the predetermined path, but actually there's no material there anymore. So it basically welds in the air, which means that the wire from the welder still is pushed out, and the spark will still happen between the wire and the base material, but because it will be so far away from the nozzle, and for the length of travel of the wire, it will basically just spit molten wire all over the place, and you won't end up with the right weld for where you intended. Or so that's one case. The other one is where literally the robot head or the welding torch hits the material, and then that also will go ugly very quickly. So unfortunately, for these reasons, it is very, very difficult to introduce robots into structural steel, and you need someone to monitor it. So you're not benefiting from the automation that robots provide in other industries. So you'd still have to have someone on the shop floor observing the robot to make sure there's nothing wrong happening with it. So again, you're not saving money, you're actually adding costs. Another reason, I'd say the third one on the list, is the fact that structural steel is quite long. So if you have a beam which is 8 meters long, 12 meters long, you would probably need either two robots, one on each end, because the majority of the fabrication is done at the ends of the beams, or a robot on a single track. So whichever way you go, you're still doubling up on the costs, because the track is quite expensive, and having two robots obviously is also quite expensive. And then the fourth reason is down to the fact that someone still has to attach the plates, the fittings, to the main beam. And again, there are companies that are trying to automate it using robotic arms with an electromagnet at the end and positioning the plates, the fitting to the right place. But to do that, you again have to add more robots, and you then really overcomplicate the whole process. Whereas this is again an area that is very natural and something that humans do with ease. Pick up a plate, read a fabrication drawing, put it onto the right place, and then tack weld it. So unfortunately, no matter how good robots are for other industries, for structural steel, unfortunately they're not so wonderful. They do have their downsides, and unfortunately these downsides at the moment outweigh the benefits. I guess I could probably come up with a few other minor reasons. But on the other hand, let's talk about the positives. So the positive that I keep talking about is the fact that a robot has 100% repetitiveness. So it doesn't have a good day or a bad day. It just follows the predefined tool path, which means that providing the material is in the right place, it will create perfect welds. So that's definitely a benefit. It's something that probably keeps us motivated. It's the fact that the welds are beautiful. The other thing that is happening, and that's a global trend, is the increased cost of human labor, which is strictly associated with the reduced amount of welders that are available. And as we know, the younger generation and even us, we prefer sitting behind desks rather than getting our hands dirty, which effectively means there are less and less people joining this industry and other industries that are more demanding when it comes to manual labor. So the pressure is significant, and the cost of human welders is increasing to a point where all the downsides of using a robot have to be overcome. It's something that is inevitable. Without it, I guess there will be a massive manufacturing issue globally. So someone has to come up with a solution, and we are working hard on finding that solution. So our journey to date has been more focused on 3D printing of steel. My reasoning behind that was, well, if there are others already working on automatic assembly of steel beams using the electromagnet sort of lifter and then robots to weld the beams, then why bother? Why waste our time joining that race? Let's leave that to them, and let's think about what will be the step after that. And I guess based on looking at other industries, one could easily conclude that the next thing would be 3D printing of steel altogether. So effectively, instead of making steels in the mill and then fabricating them, you could take a robot to site, just provided with a lot of welding wire, and it could literally print the structure in place. Now, it's a great vision, but unfortunately, we live in a financial world, and when you break it down to finances and energy consumption, unfortunately, it doesn't add up. So I guess the best way forward is a hybrid of arrangement where you would still have the bulk of the beam, i.e. the section itself made at a mill, delivered to site, roughly cut to length, sort of put them roughly together so you have a gap between the members, and then just have a robot that fills up the gap by printing steel. So we are working with UK universities and also under Innovate UK grants. We're making some progress. There's still more obstacles to overcome. But still, it is very sort of exciting avenue that we are exploring, and hopefully it will come to fruition sooner rather than later. When it comes though to simple welding, well, we are working on various solutions as to how we could adopt a robot for welding steel sections that unfortunately are all over the place when it comes to their shape. One of the ideas that we are looking at, it's something that has been introduced by the welding machine manufacturer. There are various names for it, but it's basically something along the lines of following the bead or the weld itself, or basically, like being blunt, just following the corner where you need the weld to be. There are a few ways of doing that. One of them is having a laser scanner that scans just ahead of where the welding torch is. It then quickly interprets the data and figures out where the real corner is, where the fillet weld needs to go. And then there's the other approach, which is quite clever, where based on the deposition or the welding parameters, i.e. the current, the amperage, the wire feed, and so on, you can gauge as to whether you are right in the corner or whether you're deviating from it. So that's quite clever, although quite recently we went to visit a R&D institution where we talked about whether these solutions would work for us, and they very quickly gave us the heads up, or cautioning us that we should be careful, because you can only use that technology when the weld is weaving. Therefore, instead of just going in a straight line and welding, the torch goes left, right, left, right, left, right. It's like a zigzag to create the weld. Because it's only in that motion that the software can read the parameters and understand whether the torch is deviating from the corner or not. Which is a bit of a shame, because the welds that we deposit for the majority of our work, they don't need the weaving motion, and that adds to the time and cost of welding. So it's not something that we fancy. So it seems like there aren't many options left, because even all the solutions that are available now, they're good for tracking a corner that is slightly deviating. So instead of, let's say, having a plate that is 90 degrees to the other one, not only in terms of its face, but also in its relation to the, so let's say, one of the edges. Let's say that it's 89 degrees. So someone put the plate slightly at an angle, but you still start in the corner, and then when you use that technology, it will realize that actually this plate is put at an angle and it needs to sort of change its path. So it works when you start in a known location and then the welded corner deviates, that's fine. But with one of the issues that I mentioned, with the web of a beam being like altogether moved, displaced by, let's say, 4 millimeters, then that won't work, because the welding torch would reach the corner of the web, and let's say it's 4 millimeters further. It's too much as for a correction in one go. So if that 4 millimeters was spread over, let's say, 200 millimeters, that's fine. It will understand that it's deviating. Whereas here, it's displaced altogether. It's not just deviating. So yeah, it just seems like the technology that is available just won't work again for structural steel. This brings us down to the conclusion that we probably have to invent our own solution, and we're already working on it. And hopefully it could be a new chapter for us as a company, because we could then start offering this solution to other steel fabricators. So we would become basically a robotic company, and that's something we really look forward to. It is part of what I did at university, mechanics, and part of that we did have a lot of robotics, more the kinetic and dynamic side rather than programming them, but still it's something that I covered at university, and we do have the know-how in-house to work on it and fine-tune this process. So watch this space. If you want to find out, please get in touch. We will be coming up with a solution that hopefully could be used by others. If you need more information, or if you're interested, just drop me a line and I'm more than happy to talk about it. So these are my thoughts on why robots can't be adopted in the structural steel world yet. Hopefully we will be able to somehow change it. Please remember to subscribe to our podcast so you don't miss out on all the future podcasts, and you can also catch up on the past. And see you in the next podcast. Thank you.